In this lecture, we will be talking about how to calculate a confidence interval and what it means. The objective of a confidence interval is to estimate something about a population which you cannot measure directly, often because the population is too large. In this lecture, we will be estimating a population mean, mu, or average, when the population standard deviation sigma is known. A population may be the collection of all Portland State students, or the collection of all ants in an anthill, or the collection of all cancer patients in the world. I hope you get the point. There are usually a lot of things in a population, and the population includes everything of that type. Since populations are so large, our strategy in statistics is to take a much smaller random sample from the population and use the data from that sample to create our confidence interval. If, for example, we wanted to measure the average hours spent studying for Portland State University students, it would seem very difficult to take a sample of 30,000 students, which is the approximate population of PSU, and calculate values from that. 30,000 students is very unmanageable. It would be nearly impossible to get 30,000 students to respond to a survey, for example. So instead, we'll make sure that we randomly sample about 30 students, or maybe 50 or 100 students, can be whatever sample is most manageable. We'll sample that many students from the greater population, and we'll use that sample to make our estimates. In this case, what we're really trying to estimate is the population mean, mu. We don't know it because we can't access all 30,000 students and ask them how often they study or how many hours per week they study. So mu in this case is unknown. For the sake of this example, let's assume that we know that the standard deviation from student to student is about 5 hours. So we gather our sample, we'll say 30 students this time, and we calculate our sample average, which we call x bar, just x with a bar over the top, and we calculate that to be about 10 hours. The sample size in this case, which we refer to as n for shorthand, was 30. Now that we have some information from the sample, what do we do with those statistics? That x bar equals 10, what are we supposed to do with that? We call x bar our best estimate for mu, the population mean. If you think about it, if you're trying to estimate the average of an entire population, the average of a sample from that population is a good place to start. So that's what we call our best estimate, 10. In statistics, we know that we're not always going to sample perfectly. In other words, we might get a sample that studies a little bit more often or a little bit less often than the typical average of the entire population. So we create what we call a margin of error. A margin of error is like wiggle room. It gives us the opportunity to make a statement plus or minus a certain amount so that we can be more confident in our outcome. In this case, the z number stands for the number of standard deviations for our given confidence level. We'll talk about that again in a second when we create the formula. From the problem before, we know that sigma, the population standard deviation of hours studied per week, was 5 hours, and the sample size n was 30. We're going to need both these numbers to calculate the margin of error. The general formula for a confidence interval is to take the best estimate, x bar, and then add and subtract the number of standard deviations times the standard deviation divided by the square root of the sample size. You see the formula there. We take x bar plus or minus z times sigma over a square root of n. You may recall from a past lecture that sigma divided by the square root of n represents the standard deviation of the sample mean, x bar. So it's not a coincidence that we're seeing that same value again. In general, if we want to be 95% confident, which is the typical compromise in most fields that use statistics, we're going to use z equals 1.96 standard deviations. Again, from a past lecture, you may recall that in a normal distribution, 1.96 standard deviations to either side of the mean will include 95% of all observations, or 95% of the population. Again, not a coincidence. 1.96 is what guarantees us 95% confidence. For our specific example, we're going to use x bar is 10, so I substituted in right here from x bar to 10, plus or minus 1.96 standard deviations times the population standard deviation divided by the square root of the sample size. A little plug and chug math, and we get 10 plus or minus 1.79. The 1.79 is our margin of error. 1.79 says that we know we're not exactly right with our sample mean. 10 is probably not the exact mean of the population of all 30,000 Portland State students. However, if we go plus or minus 1.8 hours, or 1.79 to be more precise, we know that we'll be pretty close to being right. In fact, we'll probably be right. That's what a margin of error allows us to do. Increase our confidence even though we're giving a range of answers instead of a single answer. If you add and subtract 1.79 from 10, you get what we call the confidence interval. An interval is a range of values from a lowest number to a highest number. In this case, our interval ranges from 8.21 hours to 11.79 hours. To interpret this confidence interval, this is the type of statement we make. We say, with 95% confidence, the interval above, from 8.21 to 11.79, includes or contains the true population mean mu of study time per week for Portland State students. In other words, if we were to take 100 random samples, like we did with the first one, calculate a confidence interval from each sample, 95% or 95 of those 100 confidence intervals would include the true population mean study time somewhere inside the interval. In other words, somewhere between the lower and upper bounds of the interval. However, about 5 out of every 100 times, our random sample will lead to a confidence interval that misses the boat completely. A confidence interval that doesn't include the true population mean inside it. Of course, we'll never know if we're right or wrong, but we will know that 95% of the time we're right. And that's kind of how statistics works. We're going to have to get comfortable with the chance that we make errors. And generally, we're okay with a 5% error tolerance, which means we're okay with being wrong 5% of the time. 95% confidence is pretty high, and it's the compromise we use in many fields of statistics. Here's an example that you might see on one of my exams. We wish to estimate the mean time it takes to get to school in the morning. A sample of 36 trips to school average 15 minutes per trip, and the population standard deviation is known to be 10 minutes. Make a 95% confidence interval. In this case, we're going to have to indicate what the key information is. We know that a confidence interval is x bar plus or minus some z number times the population standard deviation divided by the square root of the sample size. So we need to make sure we get all of those numbers. Well, we know that the sample mean was given as 15 minutes per trip. We see it right here. Average 15 minutes per trip. That was the 36 trips in our sample. So we know that the sample mean is 15. We know that z for a 95% interval will be 1.96. We'll talk about other possible intervals and how we change the z number to obtain those intervals later. The population standard deviation was given to be 10 minutes per trip. And finally, the sample size, though I didn't use the word sample size in the question, we know that there were 36 trips recorded, which means our sample size is 36. So here we see the 36 trips. We see a standard deviation of 10 minutes, and I said to be 95% confident. At this point, the four things that I've underlined are the four things you'll have to find in the question so that you can calculate the confidence interval. Now that we know what we're doing, we start to plug in the numbers. X bar is 15 plus or minus 1.96 times a standard deviation of 10 divided by a square root of 36. If you calculate that out, you will get 15 plus or minus 3.27, and in interval notation, you will get 11.73 all the way up to 18.27. What this means is that with 95% confidence or 95% probability, our sample led to an interval, this interval, that contains the true population mean. There's a 5% chance that we're wrong and we missed the true population mean completely. However, 95% confidence is very confident, and we are pretty sure that the true average time it takes to get to school each morning is somewhere in this interval here. To do this on a calculator, I have a TI-84 calculator here. We're going to make sure we have the four pieces of information off to the left here. And we're going to go into our stat button. You'll see the stat button directly below the delete button. So I go stat. You get these options. Scroll over to the right to tests and go down to a Z interval. We're making a confidence interval and we're using that Z number. That's how you know we're making a Z interval. Also, the reason we use the Z distribution is because we know the population standard deviation sigma. In the next lecture, we'll learn what happens if we don't know the population standard deviation sigma. Notice you have two options here. You can input from data or from statistics. In this case, we want to input from statistics. We have the relevant statistics. Sigma was 10. X bar was 15. Our sample size was 36. And our confidence level was 0.95 for 95%. Now we calculate. Notice that it gives us to the nearest thousandth, and we see 11.733 to 18.267, which rounds to 11.73 to 18.27, which is exactly what we got before. This is how you use the calculator to quickly calculate a confidence interval when the standard deviation sigma is known.